All right, let's continue in our chapter on alcohols, okay? What we're in the midst of doing is looking at how to make alcohols from carbonyls. Last time we finished up with the Grignard attacking a carbonyl. Okay, so today we're going to look at the same kind of thing, but with a different reagent. Okay, here we're going to look at what we call reducing reagents. Okay. Reducing reagents. And that what we want to do is convert a carbonyl to an alcohol. Okay? And that kind of reaction is a reduction, isn't it? Why is that a reduction? What have we reduced? Yeah, had a double, I reduced it to a single. Okay? Okay, so that's one way to view it, as a reduction. Any other clue that it's a reduction reaction? We added hydrogen. Okay, so anytime you add hydrogen to saturate the double bond, it's a reduction. Okay? So we want to look at some different reagents to be able to do that. Okay? So the first category
Thank you.
let's look at a couple here. NaBH4 LiAlH4. Okay. This one up here is called sodium borohydride. Very popular reagent. This one down here is lithium aluminum hydride. What two things do you see, what thing do you see being the common denominator in the names?
Hydride.
Hydride. Okay. So let's look at the Lewis structure of these so we can see that common denominator. Okay, so there's sodium borohydride. And here is lithium aluminum hydride. Put all those quizzes back in the box. Okay, so you can see In both cases, you got boron and aluminum with 4 hydrogens, and they both have negative charges. If you look on the periodic table, you see that boron and aluminum are where? In the same column or the same group, okay? So they will have similar properties, okay? So when they have 4 bonds around them, that gives them a negative charge. In order to get rid of the negative charge, what it would like to do is get rid of one of these hydrogens, okay? So the reactivity of these things is for a hydrogen to leave so that those metals get back to neutral, okay? So that sets up three kinds of hydrogens. That we can look at here. Okay? We want to make sure you remember these in organic chemistry. Okay? So what are the names of these? Well, this is simply a hydrogen atom. Okay? Learned that in grade school. This here, what do we call that? Okay, you call it a hydrogen cation. Okay? Let's look at it a little bit better than that. Hydrogen, we have 1 electron
Oh, deuterated.
and 1 proton. Okay? What do I do to go to H plus? What did I do? I lost an electron. So 0 electron and 1 proton. So what else do you think we could call that?
Hydrogen. Proton.
A proton. Okay, so we'll often call H plus simply a proton. Well, we think we're going to call this one. Here we've added an extra electron. Okay, I better tell you. Okay, this thing here is called the hydride ion. Okay. See the name here? Hydride. So what do you think these things are giving off? Hydride ions. H minus. Okay? It's kicking off the hydride ion. Okay? So that's what we want to look at in our reduction reaction. Okay? So anytime you see sodium borohydride or lithium aluminum hydride, we often sometimes call it LAH. These two simply produce the hydride ion. So the chemistry of those two all boils down to H minus. Okay. So let's draw a carbonyl compound. Like this here. And suppose we reacted with the hydride ion. Where do you think the hydride ion will attack? Okay, so if you remember our Grignard reaction, remember the carbons delta plus, delta minus. So just like the Grignard, the hydrogen will attack the delta plus and move that up there. So let's draw the result of that. Give us that there. Okay, so here the hydrogen is added on, and those pi electrons have come up here as a lone pair. Do you remember what we did in the second step of the Grignard reaction? We reacted with what?
H3O.
H3O plus, which acts as what? A proton source. So the oxygen gets a proton. And we get an alcohol. Okay. So this is how the carbonyl can be reduced to the alcohol. Any questions on that mechanism? So in summary, how would you see that reagent-wise? You would see it like this here. Okay, so you would see it as a two-step reaction to give you the alcohol.
So would you want us to show the mechanism completely like that, or would you want us to just do it at the top?
Yeah, so it depends what I ask you for.
Uh-huh.
So if I ask for the mechanism, or
So,
if I just ask for the product, you would do the top.
so we're given that problem, will it always be NaBH4 or will?
So, yeah, you could use NaBH4 or lithium aluminum hydride. So let's do some other practice ones, see if we're all on the same page there. Okay, see if you can draw the products for those reactions. I'm not asking for the mechanism. I'm just asking to draw the final product. wants to come up and do the first one? Good, piece of cake. Piece of cake. Just like an interview, piece of cake. Who wants to do the second one?
I see you looking at me, I did it, you like.
It's up to you.
Sure.
No pressure.
Because as long as we have hydrogen, we can continue to see this reaction occur. So, with that being said, it will look just like yours, except I see T1.
Would you make them both like that, or you just do one?
Well, it's more hydrogen, so why wouldn't it keep happening?
That's right, do it both.
I was asking.
Do it both. So wherever you see a carbonyl, it gets reduced to the alcohol. That's why I drew two of them. Piece of cake, couldn't it?
Yeah.
Just like an interview. All right, let's look at another way to do these reduction reactions. Another way to do them is with hydrogen and something called Raney nickel. Okay. That will do the exact same thing. Raney nickel is just nickel mixed with sodium hydroxide, okay? Then we just call it Raney nickel, just a catalyst to help the reaction occur. Okay? So if you remember, it's kind of similar to this thing here. Where we hydrogenated a double bond. Remember that? Where hydrogen added across the double bond. So that's all we're doing to the carbonyl. Okay. Just using a different catalyst called Raney nickel. Okay. Any questions on that? Yeah.
So Raney nickel will still be dealing with the alcohol?
Yeah, just still give you the alcohol.
Yeah, because nickel mixed with sodium hydroxide, or what you said?
Right, right. Okay, so those are our three ways to reduce the carbonyl to an alcohol. Very popular reactions. Okay, you should do the sodium borohydride reaction in lab. Okay, let's go to our last topic of today. And that's the topic of thiols. Thiols. Okay. Thiols are also sometimes called captains. The captain of a ship. Okay. What are thiols? Okay. When you look at the word, you almost see like an alcohol in there, don't you? Okay. These are molecules that instead of having OH, have SH. Okay. And if you look, sulfur is right below oxygen, so you can imagine they have somewhat similar properties. Okay. So, what are some examples of thiols? Let's draw them out here. Okay, so these are some examples. Let's get introduced to them by learning how to name them. And they're named just like alcohols, except what do you think the ending's going to be? Thiol. Okay. So here, that was an OH, that'd be methanol. And now we have methane thiol. So pretty simple. Okay, this one here, I have to tell you where it is. It's on the second carbon. So you have 2-butane thiol. What do you think the next one is? Cyclopentane thiol. What do you think the last one is?
2,3 hexathiol. Hexathiol.
Okay, good. Two, 3 hexane dithiol. All right, so naming these things are pretty straightforward. Let's look at some properties of these. These things have interesting properties. First property is their smell. Okay? They don't have very good smell. They stink. Stink. Think of something an animal that stinks. Skunk. What do you think they have in their tails? Thiols. Okay? So one of the thiols it has is this one here with a alkene there. Okay.
Does the stink bug have that too?
I don't know.
They smell the same.
Maybe. I'll have to ask the biology teachers. Okay. So thiols generally have really bad smells. Stink. Okay. Let's look at a second property. Second property is they tend to bind to metals. They tend to bind to metals. So what do you mean by that? Well, these things have lone pair on them. So if you have a metal, you can bind to the metal and help take a metal away. Okay?
You said it could help take another away as well.
Right. So there's in the health industry, a big movement going on to what's called chelation therapy. Has anybody heard of that? Chelation. Okay, so that's what the sulfur's doing here. It's chelating to the metal. Okay, in our bodies, we get metals from breathing pollution and so on. So you get high levels of lead in your body and other things that researchers are finding. That's what leads to Alzheimer's and other things that can go wrong. So a lot of people are going to the doctor, getting intravenous and getting chelation pumped in there to pull out the metals out of their body. Okay? About $100 a thing now. Okay?
That's pretty cheap.
Okay? But they're saying, well, it's better to do that than get Alzheimer's. Once you get Alzheimer's, you're done. Okay? So, be on the lookout, metal chelation is gaining a lot of room. You've heard of that?
No, I had a question.
Oh, okay. I thought you had metal chelation.
Oh, no.
Go ahead.
I got the money for that. I got a question. It's really referring to the smell property. Why do like tomato juice? Like why does that get rid of the smell? Like, you know, if you get sprayed by a skunk, you're supposed to like take a bath in like tomato juice. Like why is that?
What's going on there? The tomato has oxidizing agents, so it's oxidizing the thiol to another functional group, so it doesn't smell. So you've heard about the tomato therapy? Did you ever use it?
No. They say I have.
Okay. It's something to keep in mind.
I did oatmeal therapy when I was a little kid. Chicken pot.
Oh, really?
Yeah, that was fun.
That sounds Well, this is one of the reasons why, this is the main reason why thiols are called mercaptans. Do you see a metal in there?
Mercury.
Mercury. Okay. So thiols can bind very well to mercury and help take away the mercury. Okay, this is one of the ways, one of the first things to do if you ever have a mercury spill in the lab, such as breaking the thermometer or something like that. Okay, don't try to sweep it up with a paper towel or use your hand, because mercury is very toxic, especially in the vapors. Well, you put on there a thiol, okay, kind of quenches the mercury. It binds to it. You can sweep it into a container and take it away. Okay. So that's where they got their reputation from, and so they're oftentimes called the mercaptans. Okay? So that's a second property. And the third property that we'll focus on now is their acidity. Okay? Let's take a look at that over here. So let's compare the alcohol to a thiol. Okay? Remember, we looked at the acidity of alcohols last time. Okay? We found out that alcohols weren't that acidic. They typically had a pKa of around 15 to 16. Okay? And so as a result, I had to use sodium, potassium, or sodium hydride to remove that. To get the conjugate base. Okay. Well, if I come down to the thiol, I can end up using something like sodium hydroxide to remove it. To get that conjugate base. Okay. So, do you think these are more or less acidic than alcohols?
More.
Okay, they turn out to be more acidic. pKa around 10. Okay. Why do you think these things turn out to be more acidic? What do you look at? We look at the conjugate base. So this conjugate base must be what compared to that one? More stable. Why is that conjugate base more stable than the top one?
Larger.
Okay. So you're comparing sulfur to oxygen. Sulfur is a much bigger atom than oxygen. So the larger volume allows that negative charge, that extra electron, to be more stabilized. Okay. So always remember that rule. The more volume, the more stable. Okay? So that's why I can use sodium hydroxide or potassium hydroxide to deprotonate that to its conjugate base. Up here I have to use something stronger to get that. Okay? All right, so let's finish class by looking at some examples of this. See if you can draw the mechanism and the product for that reaction. Okay. So remember, when you see sodium hydroxide or potassium hydroxide, it's basically acting as OH minus. So what's the OH minus going to do? Okay, I'll call somebody out, so I'll be ready. think you can do it? Come on. Okay, good job. Okay, make sure you put the arrows the right way. It attacks the hydrogen, not the other way around. Okay. So this is how we deprotonate thiols. Okay, it's S minus. Okay, this is a key reaction, because what we're going to do on Monday is start looking at the chemistry of this. So I know how to make this. What can this do? And we'll see it can do some interesting things. Okay. Any questions as we close today?